to sketch the Bode plot for the system having g of s equal to 100 divided by s into s plus 1, s plus 2. Find gain margin, phase margin, the gain crossover frequency, phase crossover frequency. First, we need to check whether the given transfer function is in the standard form or not. That is, the standard form is nothing but time constant form. That means all the poles and zeros must be in the form of 1 plus st. So always the coefficient of s must be some value, that is called as t. So here for the first parameter is s plus 1. Here it is in the form of 1 plus st where t is 1, and here it is not in the form of 1 plus st because here instead of 1 2 is present. So we need to make it as 1. So in order to make it as 1, we need to bring 2 outside of this function. So if we bring 2 out of this, then the remaining value is 1 plus s divided by 2. So for this parameter, it will become 1 plus s by 2. So let us see the standard form. This is 100 divided by s into s plus 1 is in the standard form, but this is not in the time constant form. We need to make it as 1 plus st form. So take 2 as a common factor. Next, this factor becomes 1 plus s by 2. 1 by 2 is nothing but 0.5. We can write it as 50. Here 2 50 times. So in the numerator we will be getting 50. 50 divided by s into s plus 1 into 0.5 s plus 1. Next, in order to analyze the frequency response, we need to substitute s equal to j omega. So g of j omega will be equal to 50 divided by j omega into 1 plus j omega into 1 plus 0.5 j omega. Next, we need to find out the required data for the magnitude plot. So make a table with a factor, corner frequency and magnitude and slope. So we can divide the given transfer function. So this is the standard form for the frequency response analysis. So we can consider this as a first term, this is first factor, and this is the second factor, and this is the third factor. So we need to arrange all the three factors so that it must be in a increasing frequency values. So starting from the lower values we need to consider. So first, the poles or zeros at origin, that is the first factor. Always consider that as a first factor in order to find out the magnitude. So here 50 by j omega is the first factor. For this we need to find out the initial magnitude in order to begin the Bode plot. So we need a starting point for every graph. So here in order to plot the Bode plot graph, we need to find out the initial magnitude. How to find out the initial magnitude? Apply logarithm to this complete factor. So it will become 20 log 50 minus omega is a denominator factor, so we need to consider minus negative 20 log 50 minus 20 log omega. Here always consider the beginning frequency. There will be no corner frequency, so assume omega 1 or omega as 0.1 radian per second. So this is not omega 1, this is just omega. Omega is 0.1 radian per second. So this is 20 log 50 minus 20 log 0.1. It will become 54 dB. This is the initial magnitude. Then slope for this is in the form of 1 by s. So for 1 by s, the slope is always minus 20 dB per decade because the function is in the denominator. So it is, the slope is minus 20 dB per decade till the next corner frequency. So initial corner frequency is 0.1 till the next corner frequency is 1. So 0.1 to 1, the slope will be minus 20 dB per decade. And the second factor is 1 divided by 1 plus j omega. You can observe here, you can directly see that what do you mean by, what is the value of t here? For the first pole, t equal to 1, and here t equal to 0.5. So if we take the reciprocal of t, we'll get the frequency. 1 divided by 1 is 1, 1 divided by 0.5 is 2. So which is having the lesser frequency, that we need to consider first as a second factor. So here this function can be treated as second factor. So 1 divided by 1 plus j omega is considered as a second factor with the lowest frequency. Omega 1 equal to t is 1, 1 divided by 1 is 1 radian per second. So this is the corner frequency. Next, in order to find out the net slope, we need to consider current slope as well as previous slope. We need to add both the slopes then to get the net slope. So this is in the form of 1 divided by 1 plus st. 1 plus st is in the denominator. So it will be minus 20 dB per decade, and the previous slope is also minus 20 dB per decade. So total minus 40 dB per decade. And let us go to the third factor. The remaining factor is 1 divided by 1 plus 0.5 s or j omega. So here t is 0.5, 1 divided by 0.5 is 2 radian per second is the frequency. Next slope is current slope. For current slope is minus 20 dB per decades because it is in the denominator 1 plus st. Next previous slope is minus 40. Minus 20 minus 40 will give minus 60 dB per decade. So this is the data required to plot the magnitude plot. Next we need to calculate the values for phase angle plot. Second plot is phase angle plot. Let us write the transfer function here. And first we need to write the equation for phase angle, that is phi. So how to write this? For this function, 1 divided by j omega. First find out all the poles and zeros. Here there are no zeros, only poles are present. So first consider 1 divided by j omega. For all the denominator function we need to consider negative sign. And for 1 by j omega, how to find out the phase angle for any complex numbers means tan inverse of imaginary value divided by real value. Here imaginary value is omega. So tan inverse of omega divided by real value. No real values are present here. So real value will be 0. Omega divided by 0 gives infinity. Tan inverse of infinity is 90 degree. So for denominator function it is minus 90 degree. And then minus second denominator function. Here the imaginary value is omega and real value is 1. So tan inverse of omega divided by 1. So it will become tan inverse of omega. Next the third factor is this. So tan inverse of 0.5 omega divided by 1. So imaginary value is 0.5 omega divided by real value 1. So it will become 0.5 omega. Now for different values of omega, we need to calculate different values of phase angle. Make a column. Omega value is in the magnitude plot. The range can be determined from the magnitude plot table. That is, the minimum value is 0.1. So there were 3 corner frequencies. First one we assumed it as 0.1 radian per second. Second one is omega 1 is 1 radian per second. And the second one is 2 radian per second. So the maximum range is 0.1 to 2. So we can take 5 to 10 values greater than the range defined in the magnitude plot. So here starting from omega 0.1 to 10 we have taken. So 2 is the maximum range. Still we can take it up to 10. In order to get the smooth curve, you can take the more values for omega. So for all the different values of omega, we got 5 values, that is phase angle values. We need to find the angles in degrees. So for 0.1, so substitute minus 90 degree minus tan inverse of 0.1 minus tan inverse of 0.5 into 0.1. For that we will get phi as 98.3 degree. Similarly, substitute these values, the remaining values, in place of omega here and here. So in both omega variable we need to substitute different values of omega. Then we'll be getting different values of phase angles. So this is the data required to plot phase angle plot. So this is the semi-log sheet. We already know that the x-axis is non-linear, y-axis is linear. So here also I am considering 10 divisions as 20 dB. So this is a linear scale, all the divisions are equal. But here starting from 0.1 radian per second, this is 1 radian per second, so there is a multiplication of 10, so it is called as decade. So this is one decade and this is another decade, so it multiplies till infinity. And for magnitude plot, this 0 is this dotted line indicates the reference line for magnitude plot. First we need to mark, so let us see the magnitude plot table for the reference. So first factor is 50 by j omega, the magnitude is 54 dB. We need to mark the initial point, that is 54 dB. So if this is 40, so this is 60, in between that here we will be getting 50. So if this is 50, there are 5 divisions here, so this is 50. So here this is the 50 reading, so we need to consider 54, so 2 boxes after that. So this black point indicates 54 dB at 0.1 radian per second. So initial frequency we assumed it as 0.1 radian per second. So at 0.1 radian per second we need to mark the value of 54 dB, that is the magnitude, and mark the slope starting from 0.1 to 1 radian per second. So this is 0.1 to 1 radian per second. We need to mark the slope. Slope must be minus 20 dB per decade. So minus 20 dB per decade has an angle of what? 26 degree. So we need to consider this horizontal line, that is real axis, as a reference line, and we need to measure the angle of 26 degrees in a clockwise direction with respect to real axis. So this is a 26 degree. So from here to till it reaches 1 radian per second, we need to mark one line. So this line is with an inclination of 26 degree. That slope is minus 20 dB per decade. So it stops at 1 radian per second because this is the corner frequency for the first loop. Next, we should consider second factor. Here the slope is minus 40 dB per decade. So you can see the starting point will be the ending point of previous loop. So this is the starting point for the second slope. So starting from here, so at 1 radian per second it will start, and the slope is minus 40 dB per decade. So for minus 40 dB per decade, with reference to the real axis, the angle must be 45 degree. So we need to draw a line which makes 45 degree angle with the real axis. So this is 45 degree, we need to mark a line. So till 2 radian per second, that is the next corner frequency. So starting corner frequency is 1 radian per second and the next corner frequency is 2 radian per second. So this is minus 40 dB per decade slope. Next we should consider third factor. For third factor, the slope is 60 dB per decade. For 60 dB per decade, the corner frequency, starting corner frequency is 2 radian per second and ending corner frequency will be infinity. So for 60 dB minus 60 dB per decade, the angle will be 56 degree. So we need to measure an angle of 56 degree with respect to real axis. So this is the 56 degree. So we need to mark a line starting from 2 radian per second to infinity. So that slope is minus 60 dB per decade. You need to make use of protractor and scale in order to measure the angle. Next, this is the completion of magnitude plot. Next we can go for phase plot. So this is the table required to plot the phase plot, and these are the angles. We can put it as a scale. I am taking 40 degree difference scale. So always 180 degree minus 180 degree line should be visible. So remaining values may not be considered as a mandatory values. So you can take any type of scales, any differences of scales, but minus 180 degree must be visible. So that will be the reference line. So this is this dotted line indicates a reference line at minus 180 degree for phase plot. So now for different values of omega, we have calculated different values of phase angles. Now we need to mark all the phase angles with respect to the frequencies. So for 0.1 frequency, so this is the 0.1 frequency. At this point, this is 98.3. So if this is 100, 98.3 will come somewhere here. So this is 98.3 degree. Next one is at 0.2. If this is 0.1, this will become 0.2. So at 0.2, this is 107 degree. At 1, it is 161 degree. At 1.5, it is 183 degree. At 2, it is minus 198 degree. At 4.45, 233 degree. So we need to join all these points. And now we need to find out the crossover frequencies, that is gain crossover frequency and phase crossover frequency. Here the gain crossover frequency can be obtained where the magnitude plot crosses the reference line of magnitude plot. So this is the magnitude line, that is the gain. So here at this point the magnitude plot is crossing the reference line, that is 0 dB line. So at this point, what is the frequency that we need to note down? So starting from here, we need to see what is the frequency. So that is gain crossover frequency, that is 4.5 radian per second. This is the gain crossover frequency. Next, we need to find out phase crossover frequency. Phase crossover frequency is nothing but, here for phase plot, minus 180 degree is the reference line. So where the phase plot is coincide with the reference line, from that point see the corresponding frequency and find out the value. So this point is the intersection point to the reference line and the phase plot. So we need to check the frequency. So the frequency, phase crossover frequency is 1.4 radian per second. So these are the two parameters that asked in the question. Other two parameters are gain margin as well as phase margin. So that is the marginal value that can be increased or decreased in order to keep the system in stable state. Without bringing that to unstable state, we need to keep that in the stable state. That is a marginal value. How to find out that phase margin as well as gain margin? So we got both magnitude as well as phase plot. So starting from this omega GC, that is gain crossover frequency, draw a line downwards till it meets the phase plot. So starting from this omega GC, draw a downward line till it reaches the phase plot. So here you will be getting one point on the phase plot. So starting from this point to the reference line of phase plot. So the distance between the reference line and the intersection point on the phase plot gives the phase margin. So here by using the y-axis, that is phase angle values, we need to measure how many degrees will be getting as a phase margin. So we need to measure here 180 to 220, there are 40 degree difference is there, and also it is slightly downwards. So till here you will be getting 40 degree, and if you go near to phase angle plot, the difference will be the phase margin, that is 53 degree. In the same way, here you have omega PC, that is phase crossover frequency. So starting from this phase crossover frequency, draw a upward line till it reaches the magnitude plot. So draw one line till it reaches the magnitude plot. So here you will be getting 1 point. So the difference between this point as well as the reference line of magnitude plot. So 0 dB is the reference line, and starting from this point to this point you need to measure how many dBs of differences are there, how many dBs of gain is there, that you need to measure using this y-axis magnitude values. So this is the difference that is called as gain margin, that is 27 dB. So this complete 10 division gives 20 dB and the remaining distance gives 7 dB. So it completely gain margin is 27 dB.